Good morning, everyone. I'm Catherine Leonard. I'm the president of the Association for Women in Math, and I'm delighted to introduce to you this year's AWM-AMS Noether Lecturer. AWM established the Noether Lecture in 1980, with AMS joining as a co-sponsor in 2015 to honor women who have made fundamental and sustained contributions to the mathematical sciences. This year, we honor Laura DeMarco for her significant contributions to complex dynamics, arithmetic dynamics, and arithmetic geometry. Her work in complex dynamics opened groundbreaking directions with the introduction of the Bifurcation current to study the stable locus and moduli spaces of rational maps. In arithmetic dynamics, her dynamical analog of the Andre-Oort conjecture led to ingenious combinations of ideas from dynamics, logic, and number theory to prove certain cases. Her work in arithmetic geometry has been recognized with a 2020 Alexanderson Award from the American Institute of Mathematics for a 2000 paper obtaining the first uniform result for a complex family of curves and the Manin-Mumford conjecture. Dr. DeMarco received her PhD from Harvard University, where she is now a professor of mathematics and a Radcliffe alumni professor at the Radcliffe Institute for Advanced Study. In between, she was on the faculty at University of Chicago, University of Illinois at Chicago, and Northwestern University, where she was the Henry S. Noyes Professor of Mathematics. Dr. DeMarco has been an excellent mentor to graduate students and postdocs and has organized 3 of the GROW conferences for undergraduate women in math. Her honors include the 2017 Ruth Little Satter Prize, selection as an inaugural AMS Fellow, a Simons Foundation Fellowship, selection as an invited speaker at the 2018 ICM, and election to the National Academy of Sciences. We are so pleased to welcome her as our Noether Lecturer today, as she tells us about rigidity and uniformity in algebraic dynamics.
Thank you. Well, thank you so much for that introduction and for the opportunity to speak here on this occasion for this particular event. It certainly means a lot to me, as does, I should say, the Association for Women in Mathematics, which has been very important to me over the years, especially when I was a student and discovering mathematics as a subject, and then discovering that mathematics could be a career, and even now. So thank you, Catherine. So I want to tell you a little bit about what I'm doing now. And part of it is illustrated here. Oh, wait, I need my clicker. In this picture, I probably won't have time to tell you exactly what this is an illustration of, but it's a special case of a problem I'm thinking about today. You may recognize the Mandelbrot set in this image. Even if you don't work in this field, it's a pretty famous object. But even experts in the field would probably not recognize all of these rings and circles that are surrounding and tangled up in the Mandelbrot set. And those are some features that I'm interested in exploring. And if I have time at the end or even after the talk, I'm happy to talk to any of you about what this is illustrating. This is a picture that was just created last month. So there were features of it that were very surprising to me, and I'm still trying to figure out. So let's see. So trying to figure out how this timer is set. All right. All right. So this is an ongoing project with Myrtle Mavraki. But before I get to the new stuff, I want to go and sit back and explain some of the basic concepts in the subject of complex dynamical systems, where we study the iteration of polynomials or rational functions of one complex variable, being complex dynamics. I'll be working over the field of complex numbers. Here, I think of a map or a polynomial or a rational function f as a map from the Riemann sphere to itself. Here, C hat is my notation for the Riemann sphere. And to think of it dynamically, we're interested in studying the iterates of f, the sequence of functions, the sequence of polynomials or rational functions that you get by composing f with itself repeatedly. And what do the orbits of points look like? By which I mean you start with some given point, you apply f again, you apply f again repeatedly, and you want to know what that sequence of points looks like geometrically in the Riemann sphere or in the complex plane. And we split the Riemann sphere up into two sets. We partition it into two parts, what we call the Fatou set and the Julia set. And the names, the specific definitions do not matter for my talk today. I just wanted to mention them at the beginning to indicate that we do have this decomposition into two parts where we're interested in the complicated or chaotic part of the dynamical system, and that's what we call the Julia set, and the tame part, the understandable or the stable part of the dynamical system, which is what we call the Fatou set. But going back in time, let me tell you a little, why do we call these a Fatou set and a Julia set? Well, they're named after mathematicians, Pierre Fatou, Gaston Julia. And in fact, the specific subject of studying iteration of polynomials or complex rational functions has its origin in a competition that was announced more than 100 years ago now, so announced in December of 1915. This is an English translation of the opening paragraph of the problem. You don't need to read every line. It was just encouraging researchers to explore beyond the basics. We only knew some very basic things about dynamical systems, especially in the work of, well, not quite basic, I shouldn't say basic, but anyways, in the work of Poincaré were really the beginnings of the field of mathematics that we now refer to as dynamical systems. And this project, this competition, this problem was encouraging researchers to go beyond some of what he had done, exploring, as it says here, the global point of view, to go beyond the local point of view. By the way, I should mention that, so I'm not a historian, so I don't know the details of the history, but there's several resources out there that explain the history of the subject, one of which was published by the AMS together with the London Math Society, and I've written a reference up there, which is a book that is specifically devoted to the history of this type of dynamical system. In any case, it was this prize that prompted some important work that was done by Fatou and by Julia, which is why we use their names to describe these interesting sets that you see when you start studying the iteration of these maps. Each of them was building on the work of Paul Montel, who had introduced the theory of normal families for holomorphic functions. Now, there were only 3 submissions to the prize competition. Fatou did not submit his work, but Julia did, and Julia was given the prize. So Julia was the prize winner, and then there were 2 others. And what I'd like to talk about today is actually the work of one of the others, someone who did not win the prize, though received an honorable mention, namely Samuel Lattès. Now, Lattès, sadly, he died in 1918. He was ill with typhus, that's my understanding. So he died before the prize was awarded, and some token honor was given to his family to recognize his contribution. So I want to tell you a little bit about what he did at that time. So I'll tell you a little bit about the work of Lattès that was published in 1918. So Lattès was studying what we call functional equations, where you have collections of holomorphic or meromorphic functions, and you want to study relations, compositional relations between them. And the particular compositional relation that he was interested in was this one, where f represents a rational function, a ratio of polynomials. The curly p is our famous Weierstrass p function, where you fix some lattice in the complex plane, and the P function is some explicit, you write down some formula for a doubly periodic meromorphic function on the complex plane, given in terms of that particular lattice. L here is a complex linear function. So it's just a scaling, a complex scaling of the plane, which takes the lattice to itself. And when you have this setup, then there's a quotient of this linear map, which is f, some rational function. And he was interested in what these rational functions are. And prompted by this prize problem, was interested in the dynamics of such rational functions, f. Let me just mention, in terms of composition relations, and there are a lot of people that have studied composition relations of this sort over the years. Shortly thereafter, I should mention that Joseph Ritt, who was a mathematician here in the US, based at Columbia University, he completely classified these compositional relations in the context of polynomials. So polynomial maps, functions of one variable, complex, when you can take a given polynomial and decompose it or express it as the composition of two other polynomials. He's given us a complete classification in the case of polynomials, and that was done shortly after in the 1920s, or published in the early 1920s. And I should mention that compositional relations are very tricky, and we still don't understand, even today, we still don't have a complete description in the case when the maps are, say, all rational functions. So even in this seemingly simple setup of rational functions of one variable and studying their compositions, this form, we do not yet have a complete description. Now, we know a lot more than we did 100 years ago, but there's still some open questions about that. So I just wanted to mention there are some interesting questions there. Anyways, going back to Latez's work, we can think of this functional equation, this relationship, geometrically. Of course, the Weierstrass P function, being periodic, doubly periodic, will factor through an elliptic curve, namely the quotient of the complex plane by that lattice that we've chosen. Say, I'm calling it lambda here. So we can think of our function, or map, f, as a quotient of some endomorphism of an elliptic curve. So this linear transformation, L, this linear map, complex linear, induces a map on the elliptic curve, an endomorphism. And in fact, by calling it an endomorphism, it respects the group structure. Of course, an elliptic curve has a group structure coming from addition on the complex plane. And what is the quotient? Of course, if you pass through the elliptic curve and then pass down to the Riemann sphere, this is just identifying a point and its inverse in the group structure. So this quotient is just a 2-to-1 quotient from the torus, which I'm calling an elliptic curve because I'm thinking of it with its group structure, projected down to the Riemann sphere. And we call these maps F, these ones that you get from this kind of construction, Latez maps, exactly to honor this work that Latez did. And as I said, published in 1918, or I guess was published after his death. So this is the picture you should have in mind for this class of functions, which we call Latez maps. In fact, let me mention, this is not just abstract nonsense construction. These functions, these maps F, are very explicit, or can be made very explicit. If you choose a particular lattice, for example, let's say you take the square lattice generated by 1 and I in the complex plane. So I have this picture of a square lattice. And let's say you take your linear function to just be multiplication by 2. So you're taking the lattice and you're just scaling it by a factor of 2. So it covers, 1 square will cover 4 squares. The quotient can be written down. If you can write a presentation, you can choose coordinates on the Riemann sphere and write a presentation for f, and here is one of them. So you can see this particular rational function that happens to have degree 4. You'll notice the numerator polynomial has degree 4. And that matches the topological degree of taking 1 square and covering 4 squares by multiplication by 2. So these are very explicit. And by the way, this same example, there are many, many examples. I've given a reference at the bottom of the slide that there's a very nice article of Milner where he's describing some of this history and describing some of these examples and giving actually a complete description of, from a dynamical point of view, of these Latez maps. in this article from 2004. In any case, let me just show you, here's an image of a clip from the article itself that I found on the internet. And this page shows exactly this example. So this is one of the examples that Lattès pointed out himself. But anyways, he was interested in the dynamics. And so let me say just a word about the dynamics of these types of maps. Again, these are just linear functions, but projected down to the Riemann sphere. So the linear nature gets distorted a little when you put it on a Riemann sphere, but it's still just essentially linear. But there's one important thing that Lattès pointed out, which is the interplay between the dynamics and the group structure. The dynamics and the group structure. So again, just for concreteness, assume the linear function is just multiplication by 2. That would exist, that would preserve any lattice you chose. It doesn't matter if you take the square lattice or some other interesting lattice. Any of these complex tori will admit multiplication by 2 as an endomorphism. Now remember that a point is called torsion for a group if it has finite order. For a dynamical system, a point is called pre-periodic if it has finite orbit, meaning under repeated iteration of your map, if it eventually cycles. Okay? So there's a dynamical notion of being pre-periodic for one of these dynamical systems. And a very basic observation, which just follows from this picture that I've given you, is that a point on the elliptic curve is torsion, so it has finite order for the group, if and only if the corresponding projected point down on the Riemann sphere has a finite orbit, namely is pre-periodic for the dynamical system. Okay, so it's just a very simple correspondence between points that have finite orbit for under multiplication by 2 and points that have finite order for the group structure. Okay. So this is something that Lattès observed. And in particular, from a geometric point of view, one of his observations was that, well, we know what the torsion points are on the elliptic curve. There's this dense set of points on the curve. You take your lattice, you take all the rational multiples of your lattice points, and those will be the torsion points. They're dense inside your elliptic curve. And so they'll project to a dense set of pre-periodic points, even a dense set of periodic points, if you're only interested in the ones that come back to themselves, on the Riemann sphere. And so his observation was, well, these pre-periodic and periodic points are actually dense in the entire sphere. So, hey, isn't that interesting? From a dynamical point of view, here is an interesting observation about these dynamical systems. You can have relatively simple systems that have lots and lots of this everywhere dense set of periodic or pre-periodic points. Okay. Well, so that was Lattès' observation, and as I said, he was awarded some honorable mention for his contributions to that competition. I'm not sure people were particularly interested in this result. However, at the time, it just seemed a curious observation. This class of rational functions that Lattès was studying is very special. A typical rational function won't do anything like this. In fact, I showed you some pictures at the beginning of the Julia sets and the Fatou sets. You get these beautiful fractal pictures in the Riemann sphere. But for these Lattès examples, the Julia set is the entire sphere. So there's nothing pretty to look at. There's no lovely fractal. Of course, they didn't have the computers to draw those images at the time, but you certainly now wouldn't see any pretty fractal structure. But these examples have turned out to be very important over time as we've tried to understand the general structure of what these dynamical systems can be, and how do we classify what examples can arrive, what kind of dynamics can you really see in this class of systems. Again, just polynomials or rational functions of one complex variable. And so what I want to tell you about now is an example modern problem in which this particular class of examples, these Lattès maps, as we call them, turned out to be crucial, turned out to be absolutely crucial and play a very, very special role. But the problem I'm going to pose, the problem I'm going to put up on the slide, will a priori have nothing to do with dynamical systems. It's really a question about elliptic curves. Oh, here's the problem. So this is something I learned about in some articles of Bogomolov and Chinko, and then revisited more recently in a collaboration with Fu. And the question is the following. Suppose you're given two elliptic curves. Okay, so just C quotiented by some lattice. Each of them is of that form. Equipped with these projections down to the Riemann sphere that I mentioned earlier, where you just glue a point to its inverse. This is a 2-to-1 projection down to the Riemann sphere with any choice of coordinates on your Riemann sphere. And the question they asked is, how large is the overlap or the intersection of the image of the torsion points? So this E torse that I wrote at the bottom, that refers to the subset of torsion points in the elliptic curve. Okay? Remember, these are dense sets in these elliptic curves. So you can imagine you have this polka dot picture on one elliptic curve, this dense set of torsion points on one, and you have a dense set of points on the other, and I'm just projecting them down to the Riemann sphere, so you get these two dense sets, and I just asked the question, how much overlap do you have of these countable dense sets of points on the Riemann sphere itself? Very vaguely, I've mentioned the motivation for this problem. I don't have time to talk about all the background and where they came to this question or why they came to this question, but so I'll just say roughly it's related to some general questions about how does the geometry of this elliptic curve, the choice of the complex structure, and the subset of torsion points within it, how does that really determine E? To what extent does it determine, say, the arithmetic of E? How many torsion points do you need to know to determine what E you have? Which elliptic curve are you on? There are a number of questions of this flavor that I won't be talking about. But in any case, here's this question that they asked. All right. I guess the first question we might ask when looking at this type of problem is this finite? I mean, does this question even make sense? How large is this set, this intersection of these countably infinite dense sets on the Riemann sphere? And it turns out, yes, this intersection is actually finite. The intersection of my red polka dot set and my blue polka dot set is finite unless they're the same. By equals, I wrote unless E1 equals E2. By equals, I really just mean if the two elliptic curves are isomorphic, and if the projections via this isomorphism are the same projection, so the same coordinates down on P1, down on the Riemann sphere, if those coincide, of course, then the torsion points are the same. And that's actually the only way you can have infinite overlap, it turns out. And it's not so easy to show that. I'm not aware of an elementary proof of the fact that this intersection is finite, so I'll just mention it can be proved by appealing to the famous theorem of Raynaud, where he established the Manin-Mumford conjecture in the early 1980s. In particular, the proof, although there's no arithmetic in this slide, I'm talking about elliptic curves, complex tori, everything's over the field of complex numbers, that the proof of that, this statement, in fact, and other known proofs now of this finiteness all involve some sort of arithmetic and arithmetic geometry, which I will not be talking about. But just to let you know, I don't know any elementary proof of the fact that this intersection is finite. In any case, so the intersection is finite. But we do not know how big this intersection can possibly be. As you vary your complex structure of one of the elliptic curves or the other, as you vary the projection, you can take Möbius transformations and move your sphere around. We don't know how big you can make that intersection. That's still not known. That's still not known. However, what is known is the following. So here's a theorem that involves the work of a bunch of people and is similar to the work of a bunch of other people. And so let me just mention, here is a theorem that one can prove in this context, which is that, well, we don't know how big the intersection can be in its cardinality, but we do know that there's a uniform bound over all possible pairs of elliptic curves equipped with projections. Okay, so just to read it, there is a uniform bound M, so that, well, either the size of the intersection of these projected torsion points is no bigger than m, or they had to have been the same elliptic curve or isomorphic elliptic curves with the same projections, in which case those two projected images of torsion points are equal to each other. Okay. And just as with the Raynaud theorem that I mentioned on the previous slide, the proof of this bound involves techniques from, well, arithmetic tools, I should say, and height functions, techniques from arithmetic geometry. And you'll see that I've written something on the slide in purple beneath the statement of the theorem, which is that there were, in fact, a series of works just in the past few years that prove related statements, much more general statements. This is really just a special case of a larger story of studying subvarieties of abelian varieties and their geometric structure and how they vary in families. And there are many questions and many answers. And so I've just mentioned a few of the names of people that have contributed to some of the most recent developments in problems that are referred to as, say, uniform Mordell conjecture or uniform Onion-Mumford conjecture. So if you don't know what those are, don't worry, it's not necessary for this talk, but I do want to mention that this is all closely related to a rather large body of ongoing research related to the geometry of abelian varieties and the arithmetic in families of abelian varieties. Okay, so what does this have to do with dynamical systems? Oh, I forgot. On this next slide, I wanted to mention the record holder. I said we don't know how big this intersection can be. We only know that it's bounded by some mysterious number m, which we also don't know. But there is a record holder known, which is in some very recent work of Fu and Stoll, building on some earlier work of Stoll, where he was studying the geometry of certain genus 2 curves. In any case, in this recent preprint, they describe an explicit pair of examples of elliptic curves, E1 and E2. So they give formulas, the equations, to describe these elliptic curves, for which the intersection of these projected torsion points has size exactly 34. Size exactly 34. And this is the largest known intersection that we have. And it actually seems very likely that this will be, in fact, the maximal size. So this number m is probably, well, I wrote strictly less than, so I guess this number m is probably just, 35 or something, if that were the smallest integer. But we don't know. I guess the proofs that we have, by the way, related to finding a uniform bound do not give us an explicit number m, although in some work that I had done with Holly Krieger and Hesse Yi that I cited here on this slide, in a similar context, we came up with a bound, gave an effective argument that gives you an actual number for this uniform bound, but it's on the order of 10 to the power 100, which is huge and a whole lot bigger than the number 34. So in any case, we don't really know what the bound should be. So that the bound we can do is not very practical, but at least we know there is a bound. Okay, so what do I want to say? I wanted to relate this back to the dynamical systems that I was talking about earlier. Okay. So remember, I said that Lattès was studying the rational functions on the Riemann sphere, the rational functions, what I'm calling f and g now on this slide, which come from linear maps or endomorphisms of elliptic curves. So you could take multiplication by 2 on each of these elliptic curves and take their quotients down on the Riemann sphere, and this gives you 2 Lattès maps, f and g. And remember that these torsion images, that these projections that I've been looking at on this slide are just precisely the sets of pre-periodic points for these dynamical systems. Again, pre-periodic means that under iteration of the map, the point will eventually cycle. It eventually will become periodic, pre-periodic. So what? So one could ask, of course, More generally, if we wish, well, what about other pairs of dynamical systems? Suppose you're just handed any two maps on P1, meaning on the Riemann sphere. How do their sets of pre-periodic points compare? Is this kind of uniform bound, or the finiteness that involves the arithmetic techniques, are those special to the setting of maps that come from groups, or could it be something more general? Is this even something we could study in a much, much more general context? Here I'm only looking at maps of one-dimensional complex manifolds. What about higher dimensional maps? I mean, there are many, many questions one could ask about these pre-periodic points or periodic points. After all, the periodic points are just the fundamental objects in your dynamical system. They're exactly that we want to understand which orbits are periodic, which orbits are not, what is their structure, how are they distributed in your space. I mean, there's so many questions we could ask, but here's something fairly basic. How many periodic or pre-periodic points can two different systems have in common? So here's the question. Given F and G on the Riemann sphere, how large could be their intersection of pre-periodic points? And in any case, is a dynamical proof, for example, of a bound or a dynamical study of this problem helpful for the original problem? Maybe it's actually going to give us additional insight into what happens in the context of elliptic curves, or maybe abelian varieties more generally. So that is a question. And what do I have on the next slide? I'm not even sure. Oh, I have some pictures. Right. So here, here were two pictures of Julia sets that I showed you at the beginning of the talk. Again, now for this more general class of maps, F and G, that are not lattice maps, we get these beautiful fractal pictures of what we call their Julia sets. And these periodic and pre-periodic points are contained in these fractal sets here. And so what would it mean to study the intersection? Well, now we have some extra geometry. We have extra structure we can look at. We can look at the overlap of these fractal sets and try to understand how much overlap is there and how would we quantify that? And are there complex tools or dynamical tools that we can use to answer the question and address the intersection here? All right, so again, we don't know how big these sets can be. I should mention, we have no idea how large these can be, although we have some record holders in this context as well. But one thing we can prove is that just as in the case of the pairs of elliptic curves, there is, in fact, a uniform bound in the context of these pairs of rational functions. A uniform bound in the context of these pairs of rational functions. And so in some very recent work with Mirto Mavraki, one of the things we were able to show is that working with polynomials or with rational functions of a given degree, so I want to bound the degree of the map, we can find, at least for most pairs, a uniform bound. So the actual statement of the theorem, which I may as well read, was that in each degree, what I'm calling D, there is a uniform bound over which all pairs outside of a certain exceptional subvariety of the space of all pairs, on which we have a uniform bound on the size of the intersection. We can't have finiteness, by the way, for all F and G. Just as in the case of elliptic curves, there are examples of maps that are not the same map where you have the same sets of pre-periodic points. It turns out those sets only coincide, or that intersection is only infinite if the sets of pre-periodic points actually coincide, which it turns out is related to say that the maps share, that they're related. They're dynamically related in some way, which is also going back to my compositional relation comment much earlier, is something we still haven't fully understood, exactly when two maps have exactly the same sets of pre-periodic points. There are still some open questions there. But that would take me a little too far astray from what I wanted to say. In any case, for most pairs of maps, it turns out we do have a uniform bound. And I was going to mention on the previous slide here. So I kept this up. The comment in purple that I had made about the pairs of elliptic curves compare with the recent work related to what's called uniform Mordell, uniform Mani-Mumford, a bunch of questions and conjectures in arithmetic geometry. This result of mine with Myrto is not independent of those results in the sense that we're very much inspired by all of those results and using a lot of the same proof ingredients in this dynamical problem. So we don't know how to get bounds of this sort just with complex analytic tools, just with complex dynamical tools. We only know how to approach these problems using arithmetic ingredients. And that's why I wanted to keep this up on the slide. This is still very much in this context of arithmetic geometry tools. But there are some parts of what we're doing that involve some tools from complex dynamics, and which are more than sort of go beyond some of the arithmetic geometry techniques that we've been thinking about, and some new tools even from complex dynamics, some old tools and some new tools from complex dynamics. And as it turns out, we end up with a new piece of the proof even in the case of lattice maps. So even in the case of elliptic curves, for which you don't need dynamics, really, to study that problem, by using the dynamical approach, by knowing about lattice's work and lattice maps, one can actually get some, in fact, insight into the problem a little bit. And we do get a new proof of the finiteness of the intersection in the context of elliptic curves. We don't yet have a proof that gives a nice bound. Like, I cannot yet prove that 34 is the maximal size of that intersection, but perhaps we will be able to at some point. I don't know. Who knows? In any case, we are using some complex dynamics tools. On the next slide, I had a special case, but I think I'm going to skip that. And I want to tell you just a little bit to change gears for the last part of the talk. I want to tell you a little bit about what these complex dynamics tools are that we're using that provide some new insight into the group setting, the case of elliptic curves or even of abelian varieties, because one can generalize some of these ideas to higher dimensions. But also, from a complex dynamics point of view, it's led us to some new questions. If you recall, I put up a picture at the beginning of the talk of the Mandelbrot set with some tangled strings around it. And these questions that we've been thinking about have led us to some questions that we also can't answer, but questions about complex dynamics that are somewhat mysterious and some new direction that we'd like to think about that I might get to. So, okay. What am I even talking about? What aspect of complex dynamical systems am I referring to? I'm specifically referring to the theory of stability, the theory of stability and bifurcations in families of polynomials or families of rational functions. Again, dynamical systems of one complex variable, but now in a family. So what do I mean by a family here? What I've written on the slide is I'm calling F now a collection of maps. So F is not just one map defined over the complex numbers, but a collection of maps parameterized by some lambda in some complex manifold. Here, my complex manifold, my parameter space, I'm calling X. And I'd like to think of it as just some complex algebraic curve. Maybe it's just the complex plane. Okay, so the simplest setting, quasi-projective complex algebraic curve. Okay, you can imagine that X is just the complex plane. All right, and so F, given as a family of such systems, really you can think of as a map on all of the copies of the Riemann sphere at once. So vertically, a vertical slice in my picture is a Riemann sphere. So on every fiber, I have one map, and then I can think of F as really this map on a complex surface, which is the product of X, my parameter space, with my dynamical space, P1. And stability, dynamical stability, means, in short, that periodic points of your system don't collide with each other. But we'll say that a family of dynamical systems is stable if the periodic points remain distinct as you vary your parameter a little bit. Dynamical stability means a lot of things. So this is just a sort of a quick version of the notion of stability. Dynamical stability usually is introduced as the concept where, under small perturbation, all of the nearby maps are really the same, what we call topological conjugacy. There's a homeomorphism on the underlying space to itself that is just a change of coordinates from one map to the other. And it turns out this kind of weaker notion of stability, where I just want to keep the periodic points from bumping into each other, is actually turns out to be essentially equivalent to a notion of that flavor. So I won't go into all the details, but this really is a dynamical notion of stability. So what I'm really saying is that, remember, you have for each F, for each map, you have a complicated, perhaps very fractal Julia set, and you have lots of periodic points in that Julia set, dense in that Julia set. And everything is holomorphic. Everything is complex analytic. So those points, these individual points, by the implicit function theorem, are just moving holomorphically in the Riemann sphere as you vary your parameter. And so what I'm saying is this picture here is supposed to represent the graphs of those periodic points moving holomorphically with the parameter lambda. And as long as they don't bump into each other, we say the family is stable. Okay? And so where they're not stable is if you have some rogue periodic point here that's just somehow crashing through and colliding with the others. And that certainly happens. That certainly happens in practice. Most families are not stable, at least not stable on the entire parameter space. So here's an example, famous example, related to the picture that I started my talk with, the Mandelbrot set. If the family is the family of quadratic polynomials, this particular family, f of z is z squared plus lambda. Remember, lambda is my parameter. If x were the complex plane, so this parameter space is now all of the complex plane. What is this Mandelbrot set a picture of? The boundary of the Mandelbrot set is precisely where stability fails. There's some fractal set in the parameter space which is reflecting where stability fails. It's what we call the bifurcation locus for this family. In particular, all of those periodic points that happen to be in the Julia set, when you're either in the interior of the Mandelbrot set or the exterior of the Mandelbrot set, the picture looks like the nice black curves forming some kind of near something like a foliation, where the periodic points are all moving nicely next to each other and not bumping into each other. But as soon as your parameter passes through the boundary of your Mandelbrot set, you start having collisions like this red periodic point that's bumping into the others, and that's creating complicated, interesting dynamics. So actually, the Mandelbrot set is our sort of fundamental example of a family of such dynamical systems, which is bifurcating, and here's an example. It's just, a pictures in this sense, where periodic points are colliding with each other. Now, I should mention, I said most families are not stable, and I mean that in a technical sense. It was proved by McMullen in his PhD thesis that families, essentially all families bifurcate in this context. If you take a family, as I've described, parametrized by a complex algebraic curve, x, then the only way it can be stable, is if it's a trivial family, or, I'll say what I mean by trivial, or a family of lattice maps. The lattice maps that I mentioned earlier, those special maps that come from elliptic curves. If you take a family of elliptic curves, you vary the complex structure on the elliptic curve, that will change the dynamics. It will change the complex structure, as it were, of the map, of the function. And that turns out to be stable family. Those periodic points, torsion points on the elliptic curve, if your family's varying nicely, those torsion points don't crash into each other. Similarly, down on the Riemann sphere, those periodic points don't crash into each other. And you get some nice, beautiful foliation picture of your product space that I've drawn in blue here. Or if your family is trivial, it's always the same map, of course, then you have this sort of constant picture. Isotrivial just means under change of coordinates, it's essentially constant. So McMullen proved that if you take any other family, write down any family of rational functions, unless you're unlucky and it's trivial or a lattice family, you will see pictures like you see here with this Mandelbrot set. You will see bifurcations. So most families bifurcate. That's the conclusion of that. OK, so what does this have to do with what Mirto and I were doing, or about pairs of elliptic curves and two maps? Well, one can look at this notion of bifurcation and really study this, I don't know what to call them, pseudo-foliations of this surface, this complex surface coming from the periodic points. What do these periodic points look like? And what is the structure of these objects more geometrically? So one thing that I was looking at, which we actually use in our arguments some years ago, is what happens when you just take some other algebraic curve, maybe unrelated to the dynamics. I'm calling it P here. I'm thinking of it as a section over the projection down to the base x, but just some algebraic curve inside this surface. And one could ask, how does just some given arbitrary algebraic curve interact with this periodic semi-non-foliation thing that I have coming from all the periodic points? And it turns out that if just some arbitrary algebraic curve avoids collisions with all of the periodic points of the map. So it might look like in my picture that I have this green curve P, which is far away from all the periodic points of F throughout the whole family. Or maybe not far away, maybe it's actually very close, but it doesn't crash through any of those points. Then it turns out, again, that is very unlikely. The only way that can happen is if either that curve is one of the periodic points itself, in other words, it's part of this foliation-like structure, or the family had to be trivial, and that was just a constant point. It turns out that's the only thing that can happen. In other words, the periodic points of a family of maps are just swarming and moving around all over the space. They're bifurcating by McMullen's theorem, so they're crashing into each other, but they're also crashing into everything else. And so these periodic points really have to move around a lot in families. That's the upshot of this. The periodic points move around a lot in families. There was, I should say, going back to the context of elliptic curves and those lattice maps that I started the talk with, such a statement was already known in that context. Even where the family is stable, there are some interesting things to understand about which leaves of the foliation are algebraic and which are not. And it turns out that only the torsion leaves, the ones coming from pre-periodic points, can be even described as an algebraic curve in this surface. And that was already known. And this is, in some sense, a dynamical generalization of that fact. In any case, it turns out this is related to what we were doing, because to study the questions about pairs of maps, remember I was interested in two elliptic curves, or two dynamical systems, two different ones, in some sense thought of as on the same space, then of course what we want to know is how things interact and what's the overlap of the various periodic points, how many collisions can you have, should it be finite, is it uniformly bounded, what is the interaction? And it's helpful to always work in families and to think about what happens in families. And so, for example, in my picture here, we have in black and red the periodic points, say, of one family of dynamical systems, and then in green, the periodic points of some other family of dynamical systems. Now, since the green ones aren't crashing into each other, I'm imagining those are, say, lattice maps. Those might very well be from some family of elliptic curves. And so one can apply these arguments where collisions must happen unless the families are stable to this setting of two different maps overlapping each other. And these are really the ideas that go into the proof. I won't say much more about that. Perhaps I should just simply give you some kind of definition. So here's what we've been studying most recently, and which has led a concept which has led to some interesting new questions in complex dynamics. So again, I defined a notion of stability for one family of dynamical systems. And it's a classical notion. To say the periodic points don't collide means you can follow them, so the nearby maps are conjugate, at least on their Julia sets. We're interested in what we call a pairwise notion of dynamical stability, where you have two families of dynamical systems, and we'll say the pair is stable with respect to each other, if their respective periodic points do not collide with each other. So the periodic points of the two distinct families are either moving together in some nice foliation or stay far away from each other. So they don't collide. They don't collide. And there are some settings that are known. I wrote down in purple in the bottom of the slide. I put well-known with a question mark example because I'm not sure people were really thinking of it in this way, but it's certainly known in the literature that if you take the foliations coming from two different families of elliptic curves and you see how they intersect with each other, coming from the torsion points of two different families of elliptic curves, well, either the two families are really the same family, and so the foliations coincide, or they're forced to cross each other. So you cannot have sort of some partial coincidence and some other mess somewhere else. Or anyway. So you either have, they all cross each other, all of these curves cross each other, or the curves actually have to coincide. And it's a similar thing that we're doing, except with more general families. And keep in mind that in general, families of dynamical systems don't look anything like the green curves. They would look like the red and the black curves all tangled up with each other. OK, so the last, I guess I have to stop. I see now that it's, OK, 10:56. So just to finish, the last slide that I have was some kind of sketch of the proof. So I wanted to mention some of the ingredients that go into what we're doing. I said that our proof is not purely complex analytic, although it's led to what I consider interesting questions in complex dynamics. I have to say it like it is, which is that actually we're using a lot of machinery from arithmetic geometry to study families of polynomials on P1. I'm calling it a big black box because I don't have time to talk about it at all today, although I'd love to. There's some wonderful machinery that's been developed exactly to study families of dynamical systems, not just over the field of complex numbers now, but in more general settings, more general fields. There's this beautiful work that was carried out by Xinyi Yuan and Shouwu Zhang in this manuscript that was released just last year, or no, 2 years ago now. I guess it's 2023 now. And so this flow chart here is just supposed to indicate some of the ingredients that we're using in our proof, and we're really building on a lot of people's work, and I'm really only talking about one tiny little piece of it, which I suppose goes into the initial box. How do we even get all this machinery to run? This is where we're using the complex dynamics, is some kind of input that goes into some big machine, and then we can carry it all out. So let me finish just by putting the picture back up, and at least just mentioning what it is a picture of, and then that's it. I'm done now. So.
Thank you so much for that beautiful talk. We have some time for questions, and there are microphones in the two kind of intermediate aisles. It would be great if everyone could hear you ask your question, so if you could use one of the microphones.
Hi. When I saw your first slide, the first thing that came to mind was, could we substitute elliptic curves for hyperelliptic curves? And then I said, oh no, there's no group action. But then these are nice algebraic curves. And they could look like calculus. Is there something to be done if we started off with hyperelliptic integrals and we're just thinking along the lines of calculus and concrete calculations?
So Sure, yes. I'm sure there's plenty that can be done, but maybe not exactly in the context, exactly because I was thinking about the dynamics and the torsion points, and that, so maybe exactly the same problem doesn't go through, but I think there are lots of contexts and lots of problems where one could try to understand intersections or interesting subsets of whichever object or what kind of overlap you have in many different contexts. So I wouldn't know exactly which problem to ask in that context, but there must be some.
But you can get curves of arbitrary genus. You still have a billion varieties attached to them.
Sure.
And away you go. And
right, so I mean, taking them in their Jacobians. So there's a lot of work about looking at families of families of curves, say in their Jacobians, and as they vary and how they interact with the torsion points. And a lot of this is known now, like uniform bounds are known in those contexts from some of the work that I was mentioning, and especially in a theorem of Kuhne, and related to some other work that I had mentioned on one of my slides, where a lot of that is now known, but just in the context of, say, their intersection with the torsion points in their Jacobians, and questions of that flavor. But I'm sure there are other questions that one could ask that have a different geometric flavor that I don't know. Yeah.
Hi. Is all of this story also true if you replace the complex numbers by different fields? Like maybe you can think of local fields like QP or the algebraic completion.
Yeah, so in some sense, the proofs are very much field independent, and that's where the uniform bounds are coming from, in the sense that initially bounds were known that were really dependent on, say, the degree of the number field over which the maps are defined, or and so one of the breakthroughs in this body of work by a number of people was to sort of get past bounds that explicitly depended on the field. So for these maps, of course, yes, I'm working over the field of complex numbers. Really, the proof starts by saying, we're not actually working over the complex numbers. We may as well assume that all these maps are defined over Q bar, and that's why we can apply all this arithmetic geometry, this arithmetic machinery, and then you get some results, and then you pass to some completion in some sense. So I'm formulating everything over C because that's what I personally cared about most, but yes, I imagine a lot of this can be done in another context, but I'm not completely sure myself, not so confident to answer your question about sort of exactly what's known and exactly what you can conclude in different cases.
This is also true for the final thing you talked about, where you were using complex bifurcation methods?
Right, there we don't have that. Right, so the machinery that we're feeding into really works in a very general context. What to feed into that machinery, however, is very complex specific at this stage. So the bifurcation theory is not developed in the p-adic context, working over local fields in general, which I think is actually a really central question now to say, well, what should that bifurcation theory be? And there is some work out there. Rob Benedetto, who's probably somewhere in the room here, is actively working on that, and others are too. And so I feel like that's a real promising direction to understand what the analogs would be.
Okay, thank you for the great talk.
Thanks.
Please join me in thanking the speaker again, and have a great afternoon.